weather radar, also called weather surveillance radar and Doppler weather radar, is a type of radar used to locate precipitation, calculate its motion, and estimate its type. Modern weather radars are mostly pulse-Doppler radars, capable of detecting the motion of rain droplets in addition to the intensity of the precipitation. Both types of data can be analyzed to determine the structure of storms and the potential to cause severe weather. During World War II, radar operators discovered that weather was causing echoes on the screen, masking potential enemy targets. Techniques were developed to filter them, but scientists began to study the phenomenon. Soon after the war, surplus radars were used to detect precipitation. Since then, weather radar has evolved on its own and is now used by national weather services, research departments in universities, and in television newscasts. Raw images are routinely used, and specialized software can take radar data to make short-term forecasts of future positions and intensities of rain, snow, hail, and other weather phenomena. Radar output is even incorporated into numerical weather prediction models to improve analysis and forecasts. History. During World War II, military radar operators noticed noise in returned echoes due to rain, snow, and sleet. After the war, military scientists returned to civilian life or continued in the armed forces and pursued the work in developing a use for those echoes. In the United States, David Atlas, at first working for the Air Force and later for MIT, developed the first operational weather radars. In Canada, J.S. Marshall and R.H. Douglas formed the Stormy Weather Group in Montreal. Marshall and his doctoral student Walter Palmer are well known for the work on the drop size distribution in mid-latitude rain that led to understanding of the ZR relation, which correlates a given radar reflectivity with the rate at which rainwater is falling. In the United Kingdom, research continued to study the radar echo patterns and weather elements such as stratiform rain and convective clouds, and experiments were done to evaluate the potential of different wavelengths from 1 to 10 centimeters. By 1950, the UK company EKCO was demonstrating its airborne cloud and collision warning search radar equipment. In 1953, Donald Staggs, an electrical engineer working for the Illinois State Water Survey, made the first recorded radar observation of a echo associated with a tornadic thunderstorm. Between 1950 and 1980, reflectivity radars, which measure position and intensity of precipitation, were incorporated by weather services around the world. The early meteorologists had to watch a cathode ray tube. During the 1970s, radars began to be standardized and organized into networks. The first devices to capture radar images were developed. The number of scanned angles was increased to get a three-dimensional view of the precipitation, so that horizontal cross-sections and vertical cross-sections could be performed. Studies of the organization of thunderstorms were then possible for the Alberta Hail Project in Canada and National Severe Storms Laboratory in the U.S. In particular. The NSSL, created in 1964, began experimentation on dual polarization signals and on Doppler effect uses. In May 1973, a tornado devastated Union City, Oklahoma, just west of Oklahoma City. For the first time, a Dopplerized 10 cm wavelength radar from NSSL documented the entire life cycle of the tornado. The researchers discovered a mesoscale rotation in the cloud aloft before the tornado touched the ground. The tornadic vortex signature. NSSL's research helped convince the National National Weather Service that Doppler radar was a crucial forecasting tool. The super outbreak of tornadoes on 3–4 April 1974 and the devastating destruction might have helped to get funding for further developments. Between 1980 and 2000, weather radar networks became the norm in North America, Europe, Japan and other developed countries. Conventional radars were replaced by Doppler radars, which in addition to position and intensity could track the relative velocity of the particles in the air. In the United States, the construction of a network consisting of 10 cm radars, called NEXRAD or WSR-88D, was started in 1988 following NSSL's research. In Canada, Environment Canada constructed the King City Station with a 5 cm research Doppler radar. By 1985, McGill University Dopplerized its radar in 1993. This led to a complete Canadian Doppler network between 1998 and 2004. France and other European countries had switched to Doppler networks by the early 2000s. Meanwhile, rapid advances in computer technology led to algorithms to detect signs of severe weather, and many applications for media outlets and researchers. After 2000, research on dual polarization technology moved into operational use, increasing the amount of information available on precipitation type. Dual polarization means that microwave radiation which is polarized both horizontally and vertically is emitted. Wide-scale deployment was done by the end of the decade of the beginning of the next in some countries such as the United States, France, and Canada. In April 2013, all National Weather Service NEXRADs were completely dual polarized. Since 2003, the U.S. National Oceanic and Atmospheric Administration has been experimenting with phased array radar as a replacement for conventional parabolic antenna to provide more time resolution in atmospheric sounding. This could be significant with severe thunderstorms, as their evolution can be better evaluated with more timely data. Also in 2003, the National Science Foundation established the Engineering Research Center for Collaborative Adaptive Sensing of the Atmosphere, a multidisciplinary, multi-university collaboration of engineers, computer scientists, meteorologists, and sociologists to conduct fundamental research, develop enabling technology, and deploy prototype engineering systems designed to augment existing radar systems by sampling the generally undersampled lower troposphere with inexpensive, fast scanning, dual polarization, mechanically scanned and phased array radars. Main types of radar outputs. All data from radar scans are displayed according to the need of the users. Different outputs have been developed through time to reach this. Here is a list of common and specialized outputs available. Plan position indicator, since data obtained one angle at a time. The first way of displaying them has been the plan position indicator, which is only the layout of radar return on a two-dimensional image. One has to remember that the data coming from different distances to the radar are at different heights above ground. This is very important as a high rain rate seen near the radar is relatively close to what reaches the ground, but what is seen from 160 kilometers away is about 1.5 kilometers above ground and can be far different from the amount reaching the surface. It is thus difficult to compare weather echoes at different distance from the radar. PPIs are afflicted with ground echoes near the radar as a supplemental problem. These can be misinterpreted as real echoes. So other products and further treatments of data have been developed to supplement such shortcomings. Usage, reflectivity, Doppler and polarimetric data can use PPI. In the case of Doppler data, 2 points of view are possible, relative to the surface of the storm, when looking at the general motion of the rain to extract wind at different altitudes. It is better to use data relative to the radar, but when looking for rotation or wind shear under a thunderstorm, it is better to use the storm relative images that subtract the general motion of precipitation, leaving the user to view the air motion as if he would be sitting on the cloud. Constant altitude plan position indicator to avoid some of the problems on PPIs. The constant altitude plan position indicator has been developed by Canadian researchers. It is basically a horizontal cross-section through radar data. This way, one can compare precipitation on an equal footing at different distance from the radar and avoid ground echoes. Although data are taken at a certain height above ground, a relation can be inferred between ground stations reports and the radar data. CAPPIs call for a large number of angles from near the horizontal to near the vertical of the radar to have a cut that is as close as possible at all distance to the height needed. Even then, after a certain distance, there isn't any angle available and the CAPPI becomes the PPI of the lowest angle. The zigzag line on the angles diagram above shows the data used to produce 1.5 kilometers and 4 kilometers height CAPPIs. Notice that the section after 120 kilometers is using the same data usage since the CAPPI uses the closest angle to the desired height at each point from the radar. The data can originate from slightly different altitudes, as seen on the image, in different points of the radar coverage. It is therefore crucial to have a large enough number of sounding angles to minimize this height change. Furthermore, the type of data must be changing relatively gradually with height to produce an image that is not noisy. Reflectivity data being relatively smooth with height, CAPPIs are mostly used for displaying them. Velocity data, on the other hand, can change rapidly in direction with height, and CAPPIs of them are not common. It seems that only McGill University is producing regularly Doppler CAPPIs with the 24 angles available on the radar. However, some researchers have published papers using velocity CAPPIs to study tropical cyclones and development of NEXRAD products. Finally, polarimetric data are recent and often noisy. There doesn't seem to have regular use of CAPPI for them, although the SIGMET company offer a software capable to produce those types of images. Real-time examples: McGill University. Environment Canada. Vertical composite. Another solution to the PPI problems is to produce images of the maximum reflectivity in a layer above ground. This solution is usually taken when the number of angles available is small or variable. The American National Weather Service is using such composite as the scanning scheme can vary from 4 to 14 angles, according to the need, which would make very coarse CAPPIs. The composite assures that no strong echo is missed in the layer, and a treatment using Doppler velocities eliminates the ground echoes. Comparing base and composite products, one can locate virga and updraft zones. Real-time example: NWS Burlington radar. One can compare the base and composite products. Accumulations. Another important use of radar data is the ability to assess the amount of precipitation that has fallen over large basins. To be used in hydrological calculations, such data is useful in flood control, sewer management and dam construction. The computed data from radar weather may be used in conjunction with data from ground stations. To produce radar accumulations, we have to estimate the rain rate over a point by the average value over the point between one ppi, or CAPPI, and the next, then multiply by the time between those images. If one wants for a longer period of time, one has to add up all the accumulations from images during that time. Ecotops Aviation is a heavy user of radar data. One map particularly important in this field is the ecotops for flight planning and avoidance of dangerous weather. Most country weather radars are scanning enough angles to have a 3D set of data over the area of coverage. It is relatively easy to estimate the maximum altitude at which precipitation is found within the volume. However, those are not the tops of clouds, as they always extend above the precipitation. Vertical cross-sections. To know the vertical structure of clouds, in particular thunderstorms at the level of the melting layer, a vertical cross-section product of the radar data is available. This is done by displaying only the data along a line from coordinates A to B, taken from the different angles scanned. Range height indicator. When a weather radar is scanning in only one direction vertically, it obtains high-resolution data along a vertical cut of the atmosphere. The output of this sounding is called a range height indicator, which is excellent for viewing the detailed vertical structure of a storm. This is different from the vertical cross-section mentioned above by the fact that the radar is making a vertical cut along specific directions and does not scan over the entire 360 degrees around the site. This kind of sounding and product is only available on research radars. Radar networks. Over the past few decades, radar networks have been extended to allow the production of composite views covering large areas. For instance, many countries, including the United States, Canada, and much of Europe, produce images that include all of the radars. This is not a trivial task. In fact, such a network can consist of different types of radar with different characteristics such as beam width, wavelength, and calibration. These differences have to be taken into account when matching data across the network, particularly to decide what data to use when two radars cover the same point. If one uses the stronger echo but it comes from the more distant radar, one uses returns that are from higher altitude, coming from rain or snow that might evaporate before reaching the ground. If one uses data from the closer radar, it might be attenuated passing through a thunderstorm. Composite images of precipitations using a network of radars are made with all those limitations in mind. Automatic algorithms to help meteorologists spot dangerous weather. Mathematical algorithms have been introduced in the weather radar treatment programs. These are particularly important in analyzing the Doppler velocity data as they are more complex. The polarization data will even need more algorithms. Main algorithms for reflectivity. Vertically integrated liquid is an estimate of the total mass of precipitation in the clouds. VIL density is VIL divided by the height of the cloud top. It is a clue to the possibility of large hail in thunderstorms. Potential wind gust, which can estimate the winds under a cloud using the VIL and the height of the echotops for a given storm cell. Hail algorithms that estimate the presence of hail and its probable size. Main algorithms for Doppler velocities. Mesocyclone detection. It is triggered by velocity change over a small circular area. The algorithm is searching for a doublet of inbound-outbound velocities with the zero line of velocities between the two, along a radial line from the radar. Usually the mesocyclone detection must be found on two or more stacked progressive tilts of the beam to be significative of rotation rotation into a thunderstorm cloud. TVS. A tornado vortex signature algorithm is essentially a mesocyclone with a large velocity threshold found through many scanning angles. This algorithm is used in NDXRAD to indicate the possibility of a tornado formation. Wind shear in low levels. This algorithm detects variation of wind velocities from point to point in the data and looking for a doublet of inbound-outbound velocities with the zero line perpendicular to the radar beam. The wind shear is associated with downdraft, gust fronts and turbulence under thunderstorms. That wind profile is a display that estimates the direction and speed of the horizontal wind at various upper levels of the atmosphere, using the technique explained in the Doppler section. Animations. The animation of radar products can show the evolution of reflectivity and velocity patterns. The user can extract information on the dynamics of the meteorological phenomena, including the ability to extrapolate the motion and observe development or dissipation. This can also reveal non-meteorological artifacts that will be discussed later. Radar integrated display with geospatial elements. A new popular presentation of weather radar data in United States is via radar integrated display, with geospatial elements in which the radar data is projected on a map with geospatial elements such as topography maps, highways, state, county boundaries and weather warnings. The projection often is flexible, giving the user a choice of various geographic elements. It is frequently used in conjunction with animations of radar data over a time period.